Okay, this video helps explain these Unit 5 practice problems, which are on bonding and molecular geometry. So if we take a look at this first problem, notice we have structural formulas of a reaction, and we're told, just some details about that in the reading. Then it further states, using the table of bond energies, calculate delta H for the following gas phase reaction. All right, well, when we're asked to calculate delta H, and notice our table gives us these individual bonds and the energies associated with either breaking or forming these bonds, we should think we need to use the relationship to find delta H, where we have the bonds broken minus, and I should say the sum of the bonds broken minus the sum of the bonds formed. I'm just going to write the word formed. And this is one thing I wanted to remind you of. Remember, when we have reactants, these bonds are the bonds that are broken, so these are our reactants, minus when new bonds form, it lowers the potential energy and it releases energy. So it's really the sum of the bonds that are broken in the reactants minus the sum of the bonds that are releasing energy. This is a P for products. Let me fix that. It did not look very good. So it's reactants minus products there. Okay, so let's take a look at our reaction and look at the individual bond energies. So we know we've got to look at the reactants first. So I see this double bond between the carbons. Notice in the table it has a value of 614 kilojoules per mole. There are multiple carbon-hydrogen bonds, and then I see this hydrogen-bromine bond. So my first order of business is to add up all the bonds and the reactants that are going to be broken for these new bonds to form in the product. So I've got I'm just going to use brackets. I've got I'm going to start with that double bond, 614, to break the double bond between the carbons, and then I've got 4 carbon-hydrogen bonds, and notice I have to multiply the value that goes with that, and if you notice carbon-hydrogen is 413, so I've got 413 times 4 plus, and then I've got 1 HBr bond, and I notice that's 366. Okay, so those are all my bonds that are broken in the reactants, minus the sum of the bonds formed in the products. So now I have this new single bond, which only releases 348 kilojoules per mole. I do have, if we count carefully, 5 CH bonds. So it's 5 times 413. And the final bond is a carbon-bromine bond. So notice that hydrogen and bromine substituted into that original compound when the double bond was broken. So carbon-bromine is 276. I'm just going to add it there. So I've got to sum all the products up, sum all the reactants up. When you do that, now remember this is a subtraction here, you should come up with the answer of D. Okay? Alright, let's keep moving on. Alright, number 2, we have this reaction. I notice that it's balanced, and I also see this delta H value at the end of the reaction. Anytime I notice a delta H value, I always look at the sign, because the sign tells me something really important about this reaction, and I'd see that, wow, that's a negative, this is an exothermic reaction. That might matter, so let's see. Which of the following statements about the bonds in the reactants and products is most accurate? Okay, well, we just had a problem about that. And if we go back up, remember we said it's the sum of the bonds broken, which are those reactants or the bonds being broken, minus the sum of the bonds formed, which are in the products, and that's the products that release energy. So it takes energy to break bonds. When bonds form, it releases energy. So let's see which of these wordings says it correctly. All right, A, the sum of the bond enthalpies of the bonds in the reactants is greater than the sum of the bond enthalpies of the bonds in the product. So this is saying the sum of the reactants is greater than the products. If that's true, then this would be, delta H would be positive if you have a much bigger number and then you subtract a smaller number. So A is not going to work. Let's look at B. The sum of the bond enthalpies of the bonds in the reactants, okay, so we've got reactants again, is less than the sum of the bond enthalpies of the bonds in the products. All right, now would that work? Because we're subtracting here. Would that work? And yes, I think B is a really good choice, but let's consider what's left. The ethanol involves pi bonding and thus makes the reaction exothermic. Well, we haven't learned anything about a certain type of bonding causes exothermic. It's about the relationship of how strong bonds are and then how much energy bonds release when they form. And then D, all the bonds in the reactants and products are sigma bonds. Well, that really, it actually is not true in this case because we know carbon dioxide has double bonds. And really, it's not the type of bonds that causes it to be endothermic or exothermic. It's the energy associated with bonds. So we definitely want to pick B in this case. All right, looking at number 3, the keyword lattice energy pops up. Lattice energy of MgO. So I look at that, and it's saying is higher than NAF. Okay, so they're telling me that this is a true statement. Explanation for this observation include which of the following? Okay, well, we've learned when we look at ionic compounds, we need to think of Coulomb's law. So remember, there are 2 points to Coulomb's law. The first point of Coulomb's law we need to consider are higher charges have greater attractions. And the second point is that if we have similar charges, that we would look at smaller ions would be more attracted because they would be closer together and form a stronger bond. Because the lattice energy is really telling us how strongly the ions are attracted to each other in these ionic compounds. So let's see which one of these makes sense. Mg2 plus is less positively charged than Na plus. We have the right charges here, but it's not less, it's more. All right, B, oxide is more negatively charged than fluoride. Yeah, that sounds good. C, the O2 minus ion is smaller than the fluoride ion. Well, if I look at my periodic table, even if that is a true statement, okay, because we do know, which actually we know it's not a true statement because I had to back up there a second. Fluoride has one more proton, so it has a greater effective nuclear charge. So fluoride is actually smaller, but the one thing we need to remember here is if the charges, if O2 minus is more negatively charged, that's causing a greater attraction. The size really doesn't even matter. And then D, MgO has a more complex structural lattice than NAF. Well, there's still a 1-to-1 ion ratio, and that really doesn't matter. So we do definitely want to pick B there. All right, number 4, benzene, which is this structure that is given, has an experimentally determined bond length of 1.4 picometers. Double bonds between the carbons typically have a bond length of, and let me just correct this right here. This should be 140. Okay, so I will correct that. So let's start over. We have a bond length of 140 picometers in this structure. So we're saying that structure, the bond lengths are 140. We do know that double bonds typically, and I'm just going to write this so we can keep up with our information, are typically 134 picometers, and that single bonds are 154. So we notice the shortest distance is the double bond, okay? But what do we notice that is happening in the structure we have? Well, we have 3 double bonds and 3 single bonds between the carbons. So we have a mixture of these two types. And notice the bond length is 140. So if you remember what we learned, when you have when you have a double bond that can be in more than one position, that really something like benzene is going to have resonance structures. So if we go through is it about a polar bond? Not necessarily, right? The bond length has to do with how strongly these are bonded, because the stronger they're bonded, the closer is pulling the electrons are pulling the atoms closer together. The presence of both double and triple bonds, well, that's not even a true statement. I'm not even going to finish reading that. We don't have any triple bonds. See, the carbon atoms have both sp3 and sp2 hybridization. Well, if we look at each carbon has the same hybridization. If you notice, each carbon only has sp2. There's nothing here that would have a tetrahedral shape. So that can't be true. It must be D, and that's what you really need to think about, is it's the resonance forms of the molecule. Because even though we draw it as alternating single and double bonds, it's an average of that. So that's why the bond length is intermediate between a single and a double bond. Answer is D. All right, number 5, we've got these 4 answer choices to choose from for the next few questions. All right, number 5, which diatomic species has the largest bond dissociation energy? Okay, the largest bond dissociation energy. All right, so again, largest bond dissociation energy. So large bond energy means, you've got to really think about this, it has a high bond energy. That means it's a very strong bond. So if we look at these different connections here, you would see that A, fluorine, that would be a single bond between those. I'm going to skip boron for just a minute. That should seem unusual, because that's a kind of in the metalloid group. Then we look at nitrogen, and we should know that nitrogen has a triple bond. And notice with the fluorine, it has the lone pairs around them. I use lines instead of the dots. And then with oxygen, we know oxygen has a double bond. So of those 3, which one would be the strongest bond and therefore have the largest bond dissociation energy? So for 5, we definitely want to say C, nitrogen. Triple bonds are the strongest, have the highest bond energy, and therefore are the shortest. 6, which has a bond order of 2? Well, bond order of 2 describes how many pairs of electrons are connecting the 2 atoms. So we definitely want to pick oxygen, which is letter D. And then 7, which diatomic species has 1 sigma and 2 pi bonds? Well, 1 sigma, all single bonds are sigma bonds, but to have pi bonds, we need a double or triple bond. So if I look at oxygen, that can't be the answer, because this bond would be sigma and this bond would be pi. But if I look at nitrogen, it has the right characteristics, because a triple bond is a sigma and 2 pi. So that would be a sigma, and then the remaining 2 would be pi bonds. So we want to pick C again. Okay, 8, which of the following molecules has the shortest bond length? This kind of is very similar to a question we were asked earlier, but we were asked about bond dissociation energy. So if we'll remember from that, we can look through these. We know chlorine and bromine, both are halogens. They both have a single bond connecting them. We just talked about oxygen has a double bond, and nitrogen has that triple bond. So which of those connections will pull the atoms closest to each other? And that would be A, N2, nitrogen with this triple bond. All right, number 9, which of the following compounds is ionic and contains both sigma and pi bonding? Sigma and pi covalent bonds, which is sigma and pi bonding. Okay, so I need stuff that's ionic. Now remember, ionic compounds are a connection between positive and negative ions. So let's see if we can rule anything out just from that. So I see B and C are all nonmetals, so I'm going to rule those out. And then now I'm down to A and D. If I split this up into ions, I know this is Fe3+ and hydroxide. And then I know that this is sodium ion and cyanide. So A or D both have the ionic characteristics, but do they both have sigma and pi covalent bonds? So that's when I need to look at the polyatomic ion. If I draw hydroxide as a polyatomic ion and I draw cyanide as a polyatomic ion, I'll realize that the only correct answer is going to be D, because in D, cyanide has a triple bond, so it has the pi characteristics. Hydroxide, remember, hydrogen can only form one bond, and that would be a sigma bond. All right, number 10, the electron dot structure, or we call those Lewis structures, for which of the following molecules will have two unshared pairs of electrons on the central atom. This is the time you might want to consider drawing some of these. I'd look at C. C might be the one you've drawn the most. It's tetrahedral. You might could look at that. Carbon can have some combination to have 4 bonds. So we know that there are no unshared pairs, so I would rule that one out. Also B, you've probably drawn ammonia a lot. It has one pair of unshared or one lone pair of electrons, so I'm definitely going to rule out B. And so maybe that would narrow it down to A and D, and you want to pick A. Sulfur is bent. I mean, this H2S is bent like water. And so those are our two unshared pairs of electrons on the central atom. Number 11, which of the following molecules have planar geometries? Okay, well, let's just think about what that even means. That means that all the bonded atoms are in the same plane, and if we built this molecule, it would really look flat. Okay. So, if we think about this, let's just go through each of these types of molecules, and I'm going to start with this one because we just drew NH3, so NCl3 would be the same. And this is trigonal, but it's pyramidal, okay? And if you've built this in your first year class or maybe in a model kit just recently, you'll see that it isn't flat or planar. The next one, CH3Cl, is just a slight variation of CH4. Is tetrahedral, definitely not going to be flat. All the bonds are going in every direction. It's this that's our answer, okay? If boron does not obey the octet rule, it ends up with 3 bonds only. It doesn't have any lone pairs. It's used all of its electrons. It's trigonal planar. If you built that with a model kit, or if you did a simulation on a computer, it definitely would look flat. So 11 is A. Looks like I skipped 12. Let's find 12. There we go, 12. The Lewis dot structure, which of the following molecules shows one unshared pair of valence electrons? Okay, so we can go through and, again, you might know what a few of these look like and not have to draw all of them. Draw all the ones that you're not familiar with. Okay, so if you do chlorine, it's going to have this one pair of electrons connecting them, but there's going to be, each of the chlorines is going to have 6 other electrons around it. So this has a whole bunch of pairs of electrons, so there's no way that could be the answer. If I do nitrogen, we've drawn this earlier, there's a triple bond. We're looking for one unshared pair, but this molecule is going to have 2. Each nitrogen has 1. If we do ammonia, we had this earlier. You might have already realized this is the answer. And then you have your 1 lone pair. So ding ding, that's it. It can't be carbon tetrachloride because each of those chlorines is going to look like this and have lots of pairs of electrons around it. All right, 13. Which of the following does not describe any of the molecules above? Okay, the way I like to do this is I see the choices here. I just look, instead of saying A, B, C, D, I look at all the different formulas given and I draw these molecules, or perhaps I know their shape. Like I look at CCl4, we just saw that. We know that that's tetrahedral. Okay, so that's not the answer. CO2, you might have drawn that a lot. It's carbon. It has 2 oxygens. Each has a double bond. Each has lone pairs. But I can tell since carbon has no lone pairs on its central atom, it's linear. It's not that one. So again, the question is, which of the following of these shapes does not describe any of the molecules above? So then I look at PCl3. Well, phosphorus acts like nitrogen. They're in the same group. It's going to have a lone pair with 3 bonds, which is trigonal pyramidal. That's not a choice. And then I see PCl5 is phosphorus with 5 bonds. Ooh, phosphorus with 5 bonds is called trigonal bipyramidal. So I don't see that answer there. We might have, let's look at that. And then the last one is SF6. So far we've had tetrahedral, linear, I marked those out. Trigonal pyramidal was not there, okay? Trigonal bipyramidal was not there, so I couldn't mark this out. And this last one, SF6, that has to be octahedral, so square planar. That's the one. They gave us more shape options than were even listed below, but there's not a square planar answer. So C. 14. Pi bonding occurs in each of the following except. So we're looking for an exception to pi bonding, meaning if there's no pi bonding, we cannot have, so we're looking for something that does not have a double bond or a triple bond. That's the only cases. So we're looking for, in other words, all single bonds. All right, so first of all, I would look and see, do you know if one of these has all single bonds? And I would pick D, because I can tell. We see CH4 a lot. I'm looking for all single bonds, all sigma bonds, and that would be it. If you wanted to take the time to draw all those, I would try to recommend you only draw the ones you weren't sure of, but first, in this case, I would just look for one with all single bonds. That would save you some time. All right, 15. In a molecule, which central atom exhibits sp3 hybrid orbitals? If it had sp3 hybrid orbitals, the electron geometry would be, okay, well, for sp3 hybrid orbitals, I need a central atom, okay, and I don't really want to use a C. Okay, so I'm just going to say A. I've got a central atom, and I need to have 4 things around it. So let's think, what are the choices? If it's tetrahedral, it would have 4 bonds, and that would be sp3. If it was trigonal pyramidal, it would have a lone pair and 3 bonds. That would be 4 electron domains is what we call them. And if it was bent like water, it would have 2 lone pairs and 2 bonds. So again, see, all 3 of these are combinations to have 4 domains or 4 regions around the central atom. So which one of these is the answer? Is it? It is A. Tetrahedral. And actually here for 15, when they say bent, I'm assuming they mean bent with 1 lone pair, but that will be corrected, okay, because the way this looks, there are 2 bents, and I'm sure they meant the simpler bent, but again, that wouldn't work. Otherwise, there would be 2 answers. All right, 16. Which of the following molecules has a dipole moment of 0? So dipole means polar. So in other words, if it's a polar molecule of 0 means nonpolar. It's just kind of an unusual way to say that. We know trigonal pyramidal is polar. If you draw SO2, you will see it is also polar because it's going to be bent. Nitrogen monoxide is polar because nitrogen and oxygen have a difference in electronegativities. And hopefully you'll remember the drawing before we had benzene. It is completely symmetrical and nonpolar. 16 is A. All right, for 17, of the following molecules, which has the largest dipole moment? So in other words, that means which is the most polar. Kind of the opposite of the other one, the most polar. Well, is there anything here that's nonpolar that would never be the answer? Well, I know carbon dioxide is nonpolar. We know anything bonded to itself, just 2 atoms, is nonpolar. So we have the difference of electronegativity difference between C and O and H and F. Which one would be greater and therefore be more polar? We definitely want to pick D. In this case, HF Fluorine's the most electronegative element, so that's going to have a much larger difference than the other choice. All right, moving on to 18, which of the following has a zero dipole moment? Okay, so zero dipole moment, as we saw earlier, means nonpolar. You might want to write that, so that just kind of helps you figure out what you're going to answer. So we're looking for something that's nonpolar. Okay, if you draw A is going to be linear, but because nitrogen and hydrogen have differences in electronegativities, it's going to give it an overall dipole. Not going to choose A. B, we know NH3 ammonia is trigonal pyramidal. It has an overall dipole moment because of its shape. It is polar and not the answer. C, PF5, if you draw that, you'll see, and I'll just kind of draw the sticks. This is that trigonal bipyramidal. All the fluorines bonded around are the same. There's our answer, PF5. And then NO2, you would draw that. It's going to be, I think that would be bent. Yes, bent. And so we want to pick C because it is the only one that is symmetrical and has no dipole moment. All right, moving on to 19. On 19, for which of the following molecules are resonance structures necessary to describe the bonding satisfactorily? So for a resonance structure to be needed, we need a double bond that could be drawn in more than one position. Okay, so let's look at what we have here, and we know that A can't have a double bond. All right, D, when we draw that, oxygen is going to have single bonds with the fluorines, and then for 19, you look at carbon dioxide, we always draw it with two double bonds, and that was based on formal charge, so our answer is going to have to be B. You're welcome to practice drawing that. Would be a good idea. Which of the following has the bonds arranged in order of decreasing polarity? Okay, so we know we're going from the most polar to the least polar for number 20. Okay, so if we look at these, we know that if something's bonded to itself, that's going to have an electronegativity difference of 0. So I can see that that is going to have electronegativity difference of 0. A jumps out at me because I see fluorine, hydrogen, fluorine, that's going to be a large negativity difference. Nitrogen to fluorine is going to be intermediate between these other two because they're close to each other in the periodic table. And if you just kind of glance at everything else, nothing else is in the right order, so I definitely want to pick A for 20. 21, we're given a table of electronegativities. Let's look at the question and we'll come back to that. On the basis of the information above, which of the following arranges the compounds in order of increasing bond polarity? So increasing bond polarity from the least polar to the most polar. Okay, so let's go back and look at that table. All right, so we can see that we know fluorine's the most. All right. We probably know that, chlorine is right below fluorine. It's 3.0. Carbon and sulfur are 2.5. And then we can see hydrogen is a little bit more than silicon. So let's look at the question again. If you go ahead and, really look at these carefully, and we need to subtract electronegativity. So if we subtract, if we look at A, carbon, hydrogen, the difference would be very small, 0.4. The difference between silicon and chlorine would be 1.2, and the difference between silicon and fluorine would be the highest of 1.5. So A is actually going to be our answer here. All right, looking at 22, which of the following compounds is most likely to have the greatest dipole moment? Again, that's the most polar. So I look at these and I see that's nonpolar, that's nonpolar. Even D is nonpolar, so the only answer we could pick here for number 22 is C, and that is the answer. All right, here's this covalent bonding graph. The graph above has the distance between nuclei on the x-axis and the potential energy on the y. For an unknown diatomic molecule, what would be the approximate bond length of the molecule? So the distance between the nuclei is on the x. That's what we should look for bond length. So when we look at this, we're looking here, and hopefully for 23, you would notice that it would be definitely A. And for 24, using the same graph we use on 23, what is true for the point at the lowest part of the curve? Okay, at the lowest part of the curve, this is where the bond forms, and this is when our attractive forces and repulsive forces are equal. So we definitely want to pick B here. Okay, this is where the forces have to be minimized, and in fact they're equal. So that 24 is B. All right, 25, we have PCl5. The Lewis structure of the molecule would exhibit which of the following geometries? And so if you have phosphorus with 5 single bonds, you just have to know your shapes. 25 is C. All right, 26, we have PCl3 this time. It's cooled to a solid, and X-rays are used to measure the bond angle. Which of the following is true about the value of the bond angle? Well, it's helpful here if you know the shape. So if we go ahead and draw this, we see that it's trigonal pyramidal. Okay, instead I'm just going to draw my lone pairs as lines around so it speeds this up. So we know tetrahedral is 109.5, but we have this presence of this lone pair. That lone pair, instead of a bonded atom, actually takes up more room in space, repels the bonded atoms, and decreases this bond angle. So for 26, you've got to find, we need a less than 109.5, so it looks like it could be C or D. We need to carefully read these. The bond angle would be less than because the lone pairs around the chlorine atoms are repulsive. It's not that it's the lone pairs around the chlorine atoms, it's that the lone pair on the phosphorus atom has greater repulsive force. So D is stated the best. We want to pick D. All right, 27. The diagram above is indicative to which type of alloy? So I notice I've got this one size atom, and then I see a few really small ones tucked in the gaps, and that would represent, hopefully you remember B, that is interstitial. 28, for a substitutional alloy, what must be true about the metals that make up the alloy? Well, for the substitutional, they need to, and you just have to read for the right explanation. And it is C. You want similar sizes. 29, what must be true about the lattice energies of LIF and KF? Well, remember, this goes back to Coulomb's law. First, we look at charges. Well, Li is +1, K is +1, fluorides are both the same. So the charges are the same, so it's going to be about the size of the ions. Okay, so which one of these is smaller, Li plus or K plus? Li plus is a smaller ion. It's going to be closer, smaller distance to fluoride. So let's find the right explanation. Since they both have the same charge of ions, the lattice energies must be the same. That's not true. It's about size. K has a greater number of protons. Okay, it's really not going to be about nuclear charge when we're talking about lattice energies and ionic compounds. LIF has a decreased internuclear distance than KF, meaning a smaller lattice energy for LIF. Be careful. KF has a greater internuclear distance than LIF. That's LIF. Meaning a smaller lattice energy than LIF. That is true. The greater the distance, the smaller the lattice energy. You have to be really careful. C sounds pretty good, but because LIF has a decreased internuclear distance, it has the highest lattice energy. So 29 is D. Yeah, be careful in those wordings. You really have to read carefully. And then 30, which of the following compounds would have the highest lattice energy? So we're looking for the strongest attraction. So first of all, I look at D. It's not ionic. It doesn't even come into play as an answer. Again, it goes back to Coulomb's law. Which of these metals have the highest charges? Well, that narrows it down because A is Li+, B or C both have +2 ions. And I noticed that, since the charges are the same, it's really going to be about which is a smaller ion which would be a greater attraction. So I know that Mg2 plus is smaller than Ca2 plus, and chloride is smaller than bromide. So we want to narrow that down and choose B. That's the best answer.